Many of you might believe that physics is only about simple and ordered phenomena, like the Earth in its perfectly elliptical orbit around the sun, or atoms that are in perfect crystal structures, or electric currents that flow predictably from the socket through the lamps or to your refrigerator. But physics is much more than this.
Hey everyone, so the Nobel Prize for Physics was announced a little more than a month ago by this point to Syukuro Manabe, Klaus Hasselmann, and Giorgio Parisi for
groundbreaking contributions to our understanding of complex physical systems,
with one half being awarded to these two for
the physical modeling of Earth's climate, quantifying variability and reliably predicting global warming,
and the other half to him for
the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales.
And I am really excited about it. In a way, I haven't really been in a while for three reasons. One, because I'm glad that the Nobel Prize is extending beyond the traditional confines of pure-ish physics and actually show how far-reaching physics can be if you're willing to not be reductionist for one hot second. Two, to me, it is also kind of evidence that they were scrambling for something this year because the muon G-2 results weren't as promising as people hoped them to be. I guess we can only know after 50 years. Three, is because a lot of weird physics purists are really salty about this decision, so I want to talk about it. So if you asked a rando to summarize what this year's prize was for, they say something like climate change ? Meteorology? Which they don't sound like things that you would normally hear in a physics classroom. But firstly, no, the Nobel Prize this year was more than just climate change. And secondly, even if it is meteorology, the contributions are from climate physicists. I hope I don't have to spend too much time to explain why climate physics is important.
Season yet. One of the worst rainfall disasters in US history.
But even apart from the catastrophe, the thing about climate physics is that the math required to deal with it is really, really complicated. And the Nobel Prize doesn't give awards for math because it's not a science, I guess. And climate physics sits in this region between applied math and physics, so there. And complicated math requires new mathematical formalisms, and the motivation for why you would even want to bother, in this case at least, is because of meteorology. It starts out with asking how wind currents move, and then the math required to answer that question develops in a crude manner, but then the pure mathematicians get in on it and then formalize it and start doing some really cool stuff with it. And then finally, the fundamental physicists, also known as crazy people who want to show that gravity isn't a thing, maybe, steal that math and then prove some fancy things within their own field and then remark on how interesting the parallels are between their final applications, which tend to be like really small, really esoteric stuff, and the original inspiration, which is the literal dynamics of the atmosphere. Okay, so let me give you a quick example of this. You've heard of the butterfly effect, this idea that a butterfly flapping its wings somewhere on one end of the planet can cause a devastating storm on the other end of the planet. Okay, so I wouldn't put it like that. I think a more accurate analogy is more like, imagine there's two nearly identical universes, and one where there's a devastating storm and one there isn't, and the only difference between the two is that a butterfly flapped its wings in one. I don't think this analogy helped. Point is, it was discovered, asterisk, by Edward Norton Lorentz. Wait, what? A mathematician and meteorologist who was trying to simulate the weather based on some really basic modeling, and then he found out that changing some of the initial parameters describing the system, something on the level of like the current temperature is not 24.336529 degrees Celsius, it's 24.34. And that tiny difference can lead to drastically different results. While on the one hand it means that perfect forecasting is quite literally impossible, on the other hand, it led to several decades of creating a lot of mathematical machinery and tools to do some level of forecasting, and later developing brand new objects to try and boil the entirety of this new field using some really basic definitions, and voila, suddenly we've created chaos theory. Now, you might not know why chaos theory is a big deal. Butterflies and double pendulums are one thing, but what does that have to do with protons and neutrons? It turns out that chaos theory started from computer simulations back when computers looked like this, but eventually grew because it asked more questions than it answered. Like, When is something chaotic actually? Spoilers, this question is way harder than it sounds. And part of the growth is to come up with new concepts to answer these questions, which only ended up asking even more questions. Eventually, after many mathematicians, biologists, chemists, physicists dabbled in this nascent mathematical framework, we get to this big stonking idea called renormalization flow. If you thought the shortish video was going to explain renormalization flow,
No.
but to just get the basic and really rough idea through, it's a piece of rigorous mathematical machinery that basically says, when you're looking at the big picture, there's no point in sweating the small stuff. Basically, you don't need to know where every single electron on every single atom on Earth is to tell, to a large degree of accuracy, how fast the Earth is going around the sun. Or for that matter, how fast the Earth is going to melt and fry. But the thing about renormalization is that it also made it super easy to talk about relevant information when we're looking at the universe at the fundamental level, because it provides a natural way of ignoring finer details we still don't know while still managing to describe things at scales we are currently interested in. Like those people who are trying to find out if gravity is real. Yeah, it probably is in everyday scales, but if you zoom in enough, it's probably something else entirely, and probably doesn't exist in any recognizable form. I had a point. Right, my point is you don't know what can be the source of inspiration for some ideas, and so calling those fields dumb or useless or completely disconnected from the purest pursuit of fundamental physics, whatever that means, before we can even see the field grow and flourish, is what we in the industry call a dumb move. Like, I have a feeling that a lot of lay people who are kind of invested in the progress of fundamental physics, but aren't physicists themselves really, have this attitude towards this year's prize, because I think their conception of meteorology is fancy fortune-telling, when it's so much more than that. Because overall, the Nobel Prize for this year is for complex systems, which is kind of hard to define by itself because, okay, not because it's called complex. Normally, we have this idea that in order to understand something, we need to understand its components, right? This is called reductionism. If you want to understand how organisms work, you need to understand how cells, the fundamental building block in biology, asterisk, work. But this is not always true. Sometimes you have systems where there are so many interactions, so many moving parts, so many, just everything, that you can't even keep track of what these individual cells are even doing. That even understanding how they work will not still tell you how the big system works. We can understand how cells work to a remarkable extent, but that does not mean we understand a lot of large-scale biology stuff. Because there are a million kinds of cells that talk to each other and do all kinds of crazy things. There is emergent phenomena that you simply can't just learn about in a bottom-to-top approach. In a nutshell, complex systems are where the whole seems to be bigger than the sum of its parts, and we want to understand how the whole works. And while the theme for this year's prize is very obviously complex systems, I think it's very easy for people to actually think it's climate change. So they think that everyone and everything involved is all climatology, which obviously isn't really the case. So let's talk about the fact that the Nobel Prize decided to split the award in this way. Why did this person get 50% of that delicious dynamite money? Like his prize statement says, he's a scientist who's done a little bit of everything, ranging all the way up from climate physics down to high energy physics. And I think r/physics was somewhat excited by this prize precisely because of the high energy physics thing. Because like I said before, there's a lot of mathematical overlap when it comes to complex systems, be it the weather or, surprise, the proton, which is not a fundamental particle. It has quarks inside, and quarks don't like reductionism at all because they keep complicating everything, because they keep interacting with themselves and just creating a messy complex soup, and then things just keep happening and nothing ever makes sense. You can take your reductionism over there, okay? And even they don't seem very happy about it. Oh, let's talk about you particle physicists. You thought I was letting you off the hook so easy? Nobel Prize physics purism isn't anything new. We keep hearing about it year after year, and this crowd gets especially loud whenever the prize is given to something pretty applied, like the invention of blue LEDs, or the invention of CCDs, or the invention of fiber optic communication.
This isn't really physics.
You'll hear people say,
That's chemistry.
or
Applied physics.
or
Engineering.
or whatever. But like, why it's physics? Like, the people working on it are decidedly physicists, and the people who nominated them are physicists. That's how the Nobel Prize works. And in reality, these lines between disciplines are way more blurred than the Nobel Prize makes them look, and how people normally think science works. So as far as why people are dicks about this, I have 2 theories. Let me know what you think down below. Theory 1. Gatekeepy people are gatekeepy. There's a misconception that is way more common than you think, that high energy physics is the only real physics, especially when we're talking about like pushing the frontier of the unknown, which is demonstrably false. There's a lot of frontier pushing work, both theoretically and experimentally, that is not just a high energy particle accelerator physics. I think this is super prevalent because this idea of reductionism being the only way to do real science is also super prevalent, when that's not really the case. And this is super personal for me too, because I thought for a hilariously long period of time that high energy physics is the only physics, and CERN is the only real physics place because of that. And because of that, I kind of railroaded my educational journey, if you want to call it that, and kept finding it fucking boring, because there's a lot of things that are interesting and is real physics, dare I even say pure fundamental physics, that doesn't directly revolve around what CERN is doing right now. CERN isn't the only way to do physics, kid. I'm talking about me. I am kid. Theory 2. High energy physics people are butthurt that they're hitting nothing but dead ends, and literally everything non-high energy physics is getting the attention now. The last Nobel Prize that was connected to high energy particle physics is maybe 2015 for the discovery of neutrino oscillations, but I would say that the last surefire, this is a certified high energy physics discovery, was in 2013 for the Higgs boson stuff. And nothing's happened after that, because high energy physics is stuck right now. They thought their €1 billion a year toy was going to give them a whole Toys R Us catalog of new particles, but like the state of Toys R Us today, there's literally nothing. No string theory, come back after all your founders are done winning the Nobel Prizes. While I think theory 1 is more likely than theory 2, I personally like theory 2 more because it pisses a lot more people off, and I know that because someone told this to me a long time ago and I got really pissed, and it's only taken me an entire degree to realize yes. And to be clear, none of this is meant to be shade for people who are actually working in these fields. I have many high energy friends. This is just banter. I hope you don't mind. But apart from all of the above, I think the real question is, as comes up every single year, I guess, what is the point of the Nobel Prize at all? Now, I don't have a very high opinion of the Nobel Prize. For me, it's kind of like how people react to the Grammys. Like the whole year, they'll be like, it doesn't really mean anything. It's all bullshit. And then they announce the winners, and everyone collectively lose their minds. Because the truth is, I do care about it, even if I think the whole thing is bogus. And even if the whole thing is bogus, it doesn't change the fact that people winning Nobel Prizes affects a lot of things in the real world. And the only real point to the Nobel Prizes today that I can really think of is that it's kind of like a PR service. Like the way how the Nobel Prizes even choose and distribute prizes is such a 19th century idea. Like, Alfred Nobel died in 1896, before the discovery of the electron. You think he could have envisioned the massive logistical and HR nightmare that is operating the Large Hadron Collider and its 20,000 person workforce? Like, you really think this guy could have imagined the Lovecraftian horror that is citing a paper with 300 co-authors? The prize still, in principle, awards single people, even this one, even though that's objectively not how physics works. Today more than ever. It's PR because stories about single humans are very compelling. Look at the Chernobyl miniseries, for example. And stories help with outreach and public awareness, which will lead to people being less unkind when it comes to writing and signing bills and laws that fund research institutions that do cool and interesting things. And in that regard, I am very much on board for migrating the common understanding of physics away from high energy particle physics to literally the everything else. Mostly because I think high energy physics is saturated and throwing more people and money on it isn't really the optimal solution at the moment. but partly because science isn't a zero-sum game, and giving other fields a lot of attention, financially or otherwise, can result in net good for us all. Like, I'm making a bet right now. It's going to be some breakthrough in condensed matter physics that's going to solve the whole quantum gravity debacle. Because you know what happened the last time there was a breakthrough in condensed matter physics? That's right, we formulated the Higgs mechanism that tied the best theory humans have had all up into a nice little bow. So yeah, in case it's not clear already, I'm super glad that the Nobel Prize for Physics this year went to something that a lot of people don't generally think of as physics. I'm sure someone here will disagree. Please disagree. I want attention more than particle physicists want grant money. And if you disagree with those people, argue with them. Fuck everything. The world is burning to a crisp anyway. Spend your last minutes of your sadly finite life arguing with randos on social media. Do it. I dare you. Wait, also like, share, and subscribe.
Panic on the streets